So, welcome back to the engineering chemistry course. Let us start. Before starting the today's lecture, just have a recap of the previous class. In the last class, we have discussed about the general introduction of the fuel and classification of fuel, in which we have discussed that fuels, basically chemical fuels, may be classified on the basis of their occurrence and on the basis of their physical state. On the basis of their occurrence, the chemical fuels are of two types, primary and the secondary fuel, while on the basis of their physical state, fuels are solid, liquid and the gaseous fuels, in which in the previous class we have started with the solid fuels, coal, and the formation and the types of coal we have already discussed. After that, we have started with the calorific value, definition of the calorific value and the types of calorific value, in which we have discussed about the GCV, gross calorific value, and the NCV, net calorific value. So that's all about the previous class. So let us begin with the today's class. Now look at the topics which will be covered in this class. Determination of the calorific value. There are various methods to determine the calorific value. Among all these methods, today we are going to discuss the determination of calorific value by Bohm's calorimeter, in which we will discuss about the construction of Bohm calorimeter, working of Bohm calorimeter, observation and calculation with this method, and the various corrections used in the Bohm's calorimeter. So basically we are going to discuss the complete process of Bohm's calorimeter in today's class. So let us begin. Determination of calorific value. Basically, calorific value can be determined in two ways. First, experimental methods, and second, theoretical methods. In the experimental methods, two types of calorimeters are used to determine the calorific value of the given fuel. First is the Bohm calorimeter, second one is the Junkers calorimeter. So now what is the difference between these two? Basically, the Bohm calorimeter is used for the determination of calorific value of solid and non-volatile liquid fuels, while Junkers calorimeter is used for the determination of calorific value of volatile liquid and the gaseous fuels only. That means both of the calorimeter are differ in the type of the fuel for which they are used. It is very clear now that Bohm's calorimeter are specifically used for the determination of calorific value of solid fuels and the non-volatile liquid fuels, while the Junkers calorimeter are used for the determination of calorific value of volatile liquid fuels or the gaseous fuels. Clear? Now, theoretical determination is done by the Joulon's formula, by which all types of fuels calorific value we can determine. So, determination of calorific value can be done by experimental methods or by theoretical method. Experimental method depends upon the type of the fuel. If we have the solid fuel or the non-volatile liquid fuel, then Bohm's calorimeter is used, while if we have volatile liquid or the gaseous fuel, then Junkers calorimeter will be used. For the theoretical determination, Joulon formula is used. So let us begin with the determination of calorific value by Bohm's calorimeter. This is the construction diagram of the Bohm's calorimeter. Mainly, the Bohm calorimeter contains four main parts. First is the steel Bohm, second is the silica crucible, third is the copper calorimeter, and fourth one is the air and water jacket. So let us discuss one by one all of these. First is the steel Bohm. Look at my cursor here. This is the steel bomb where I am pointing out this part is called as the steel bomb. Clear? This steel bomb consists of a strong stainless steel vessel which is capable of bearing 50 atmospheric pressure. The bomb is provided with a lid. This is the lid. The bomb is provided with the lid. Lid means its cover, which in turn provided with the 3 hole. First middle hole is for the oxygen supply. This oxygen supply, it is the oxygen valve, and 2 holes, side holes, are for the electrodes. These electrodes are further connected with the battery. Clear? And a small ring here, a small ring is fitted to one of the electrode which act as a support of silica crucible. This small ring which act as support as a for the silica crucible. Right? So this is the steel bomb. This structure is the steel bomb. Why it is called the bomb? Because the combustion reaction taking place in this compartment, that's why it is called the bomb, and it is made up of the stainless steel, that's why called steel bomb. The steel bomb contains a lid over it. The lid contains 3 holes, 2 for the electrodes and middle one for the oxygen inlet, which is called the oxygen valve, which is necessary for the combustion reaction. And one electrode contains the ring which supports the silica crucible. Now, what is the silica crucible? Silica crucible is the small container in which the fuel sample for which calorific value is to be determined is placed. So, this is the silica crucible. Silica is the refractory material. Crucible is a small dish, a small pot we can say. So, this is the silica crucible, and this silica crucible contains fuel sample whose calorific value we are going to determine. Now, to provide the connection between the electrode and the fuel sample, these are the 2 electrodes and the fuel sample, there is the magnesium wire. This is the magnesium wire. This magnesium wire, which provides the connection. Why connection is needed? It will be explained in the procedure part. Okay. Now, third one structure is the copper calorimeter. This compartment is called the copper calorimeter. This one. In the copper calorimeter, known amount of water is placed. This is the known amount of water is placed in the copper calorimeter. The opening of the copper calorimeter having 2 holes in which Beckmann's thermometer is there and the stirrer is there. This is the Beckmann's thermometer and this is the electrically operated stirrer. Beckmann's thermometer can record 1/10 degree centigrade temperature. So very minute temperature difference it can easily record. So this is the copper calorimeter in which known amount of water is filled, and this copper calorimeter contains Beckmann's thermometer and the electrically operated stirrer. Now fourth part is the air and water jacket. The copper calorimeter is surrounded with the air jacket and the water jacket. These air and water jackets are prevent any loss of heat due to the radiation. So I hope all the components of the bomb calorimeter you have clear now. I am just now repeating again. The main component of the bomb's calorimeter are steel bomb, silica crucible, copper calorimeter, air and water jacket. Now, how this bomb calorimeter works? So let us discuss the procedure of the determination of the calorific value by Bohm's calorimeter. First of all, a known amount of fuel sample is placed in the silica crucible. This is the known amount of fuel sample. It is placed in the silica crucible. The crucible is supported over the ring. This is the ring here. This one. Supported over the ring, a fine magnesium fuse wire. This is the magnesium fuse wire. This magnesium fuse wire touching the fuel sample is stretched across the electrodes. This magnesium fuse wire, and oxygen is supplied through this oxygen valve till the pressure is reached between 25 to 30 atmospheric pressure. So this much amount of oxygen has to be supplied in the Bohm's calorimeter. Now initial temperature is recorded in the Beckmann's thermometer, that is the T1 degree centigrade. This is the initial temperature. The electrodes are then connected with the 6-volt battery. These electrodes are connected with the battery, and the known amount of water is filled in the copper calorimeter. Now the current is switched on through the battery, this one battery, and circuit is completed. The current is switched on and the fuel is in the crucible burns. This fuel burns. How it started burning? Because we started the oxygen supply from here, which is required for the combustion. And when the electrodes are heated due to the electricity, the magnesium wire which is attached to these electrodes are also heated, and due to this heat energy, magnesium fuse wire burns. The burning of magnesium fuse wire liberates energy which gives the ignition temperature to this fuel. I hope you all must aware about the fact that to start the combustion of any kind of fuel, there is the requirement of some ignition temperature. So to provide the ignition temperature, the magnesium fuse wire burns. So due to the burning of this magnesium fuse wire, heat energy generated, and this heat energy provides the ignition temperature to this fuel to get start the combustion reaction in presence of this oxygen. So after the burning of the magnesium fuse wire, combustion of fuel is started. Now due to the combustion of fuel, as we have discussed in the previous class, the combustion products are formed. The mainly combustion products are carbon dioxide and water, and with these combustion product, large amount of heat energy also evolve. Now the heat energy evolved due to the combustion reaction is get passed through this steel bomb to the copper calorimeter. Now this heat energy goes here and water get started heating. So the temperature of the water starts increasing. Clear? So the total amount of heat energy liberated by combustion of this fuel is get absorbed by the water in calorimeter, and some amount of heat energy also absorbed by this calorimeter. So the total amount of energy liberated by this combustion of this fuel, that is its calorific value, is get absorbed by two. First is the water and second one is this calorimeter. So two things absorb the water, absorb the heat energy. First is the water in calorimeter and second is the copper calorimeter itself. So after the complete combustion reaction, we noted the final temperature T2 degree centigrade in the Beckmann's thermometer. Clear? So I am once again I brief up the procedure. First we started supply of oxygen valve. known amount of fuel sample is taken into the silica crucible, known amount of water is filled in the copper calorimeter. Now switch on the electricity. As we passes the electricity, the electrodes are heated. Due to the heating of these electrodes, the magnesium fuse wire are also heated and burns. The burning of magnesium fuse wire releases the energy which provides the ignition temperature to this fuel. As the fuel get ignition temperature and oxygen is already supplied, so this fuel get started its combustion reaction, and the heat energy evolved by this combustion reaction is passed through this steel bomb to the copper calorimeter, and the water in the copper calorimeter heated, and we noted down the final temperature T2 degree centigrade. So this is the brief process. Now how we calculate the calorific value? So let us look the observation first. Suppose we have taken x gram of the fuel in the silica crucible. What is the x gram? This fuel sample. Suppose the amount of this fuel sample we taken in the silica crucible is x grams. Weight of the water in the copper calorimeter, that is the known amount of water I have discussed. Suppose this amount of water is capital W grams. Now water equivalent of the copper calorimeter, suppose small w grams. What is the water equivalent of copper calorimeter? As I just now discussed that the copper calorimeter also absorbs the heat energy. So water equivalent of calorimeter means this calorimeter absorbs heat energy which is equal to some amount of water. That means this amount of water absorbs same amount of energy as the copper calorimeter. So this is the water equivalent of the copper calorimeter. Now suppose the gross calorific value of this sample is L. Initial temperature is T1, final temperature is T2. So increase in the temperature will be the T2 minus T1 degree centigrade. Now how we calculate the calorific value, gross calorific value of this fuel sample? We know that heat liberated by burning of fuel is equal to heat absorbed by water and the copper calorimeter. So total heat liberated by combustion of the fuel is equal to X multiplied by L. Why we done so? X is the total amount of fuel sample and L is the heat energy liberated by per unit mass of the fuel. So if 1 gram of fuel releases L energy, L calories, so total X gram of fuel releases how much amount of energy? X multiplied by L. So this is the total amount of heat energy liberated by complete combustion of the fuel. So this is the total amount of heat energy. This total liberated energy will be absorbed by the water and the copper calorimeter. So now we calculate how much amount of energy is absorbed by water and the calorimeter. Heat absorbed by water is equal to weight of water multiplied by specific heat of water multiplied by increase in temperature. We know that the specific heat of water is 1 calorie. So this figure is the 1. So finally the heat absorbed by water is equal to capital W T2 minus T1. Now heat absorbed by calorimeter, which is equal to water equivalent of calorimeter multiplied by rise in temperature. So it is small w T2 minus T1. So if we calculate the total heat absorbed by water and calorimeter is equal to capital W T2 minus T1 plus small w T2 minus T1. If we take common this figure T2 minus T1, then capital W plus small w T2 minus T1 calories. So this is the total absorbed energy and total liberated energy is XL. So both of these must be equal. So XL is equal to capital W plus small w T2 minus T1, and L will be equal to capital W plus small w T2 minus T1 by X calorie per gram. This is the HCV of the fuel. And from this HCV, how we can calculate the LCV? In the previous class we have discussed LCV is equal to HCV minus 0.09 H into 587 calorie per gram. So this is the LCV calculation. But somehow from this formula we cannot calculate the accurate amount of HCV and LCV. Why? Because some corrections are still required in this formula. Now, what are these corrections? First is the fuse wire correction. What is the fuse wire correction? We know the magnesium fuse wire is used to provide the ignition temperature to the fuel sample. But the heat liberated due to the burning of the magnesium fuse wire also includes the heat given out by the complete fuel. So it must be subtracted by the total heat calculated, because magnesium fuse wire burning is not the combustion energy burning. That's why it must be subtracted from the total heat value we calculate. Second correction is the acid corrections. We considered the fuel, mainly the hydrocarbon fuel, which contains carbon and hydrogen. In case the fuel also contains sulfur or the nitrogen, then during the combustion process, these sulfur and nitrogen present in the fuel forms corresponding acid H2SO4 and the nitric acid, and the formation of acids are the exothermic reactions. That means these also liberates large amount of energy, which is not the combustion energy. These are the acid formation reactions. So these values must be subtracted from the total value, because these values are not the combustion energy value or the energy released by the combustion reaction. So always acid corrections must be subtracted from the total value. Third one is the cooling correction. The time taken to cool the water from maximum temperature to the room temperature is noted. First of all, we must know what is the cooling correction. We know that in the Bohm's calorimeter, the value of HCV is determined, and by definition we know that the HCV is the calorific value when fuels combustion products are allowed to cool down at room temperature. So this cooling process, during this cooling process some heat loss is there due to the cooling process. So we must include this heat loss to the correction, because this heat loss is from the combustion energy loss. Therefore this cooling correction must be added to the temperature. So for this purpose, the time taken to cool the water from maximum temperature to the room temperature is noted. Suppose this is the T minutes, right? And the rate of cooling is dt per minute. Suppose dt temperature falls in the per minute and total time for cooling is T minutes. So the cooling correction will be the dt multiplied by T. So in all we have the three corrections: fuse wire correction, acid correction and the cooling correction. Out of these three, the fuse wire correction and the acid corrections must be subtracted from the total value, while the acid correction is to be added to the total value. So after incorporating all these corrections, the final formula for HCV is HCV is equal to capital W plus small w, T2 minus T1 plus TdT. This is the cooling correction, minus A plus F minus acid correction minus fuse wire correction. Calorie per gram is the unit, divided by X. So this is the final formula for the HCV. You must remember that cooling correction is always added, while acid correction and fuse wire correction are always subtracted from the total value. So the final formula is capital W plus small w, T2 minus T1 plus TdT, cooling correction minus acid correction minus fuse wire correction divided by X. So this is the final formula. So let us revise what we have discussed today. Today we have discussed about the determination of calorific value, in which we have discussed it can be determined by experimental methods or by theoretical method. Experimental methods, Bohm's calorimeter and Junker's calorimeter, and by theoretical methods Dulong formula is used, in which we have today discussed the determination of calorific value by Bohm's calorimeter, in which construction, working, observation and calculation and the final corrections we have completely discussed in today's class. Now it's time to learning check. Pause the video and read the question and think about the answer. For the determination of calorific value of wood, which calorimeter can be used? Bohm's calorimeter or the Junker's calorimeter? Yes, you are right. This is the Bohm's calorimeter, because wood is the solid fuel, and for determination of the calorific value of solid fuel, Bohm's calorimeter is used. So the answer is the A. Correct option is the A. That's all about the today's class. Thank you so much. Take good care of yourself and keep enjoy e-learning at home. Thank you.